This will wrap up 4-4's homework. Kind of a hodgepodge of problems. 48 is not from your homework set. I said on the last video that I wanted to include it because it's kind of a neat problem. We don't get a lot of practice on logarithmic differentiation problems. So here we have this function. We're supposed to find the derivative logarithmically. So I'm going to take ln. When we're in calculus, it is all about ln because, as you found out, derivative of natural log, calculus just works really, really well with it. So I want to take ln of y equals ln of this guy, but when I take ln of this guy, the payoff is I get 1 on ln x times ln x. Well, that's interesting. That just means that ln of y equals 1, and therefore, well, we're going to get out of this one really easily. Therefore, we want the derivative of this. The derivative of this would be 1 on y. I think we should see where we're headed with this one right now. dy dx equals derivative of 1 is 0. Multiply both sides by y, I get dy dx is 0, which would imply that x could be any value that we wanted it to be. However, x cannot be any value we want it to be because this graph only exists when x, because I can't have ln of 0 or ln of a negative, it only exists when x is greater than 0. So as simple as that problem was, we still have to consider, hey, this would tell the reader, oh, the slope is 0 everywhere. Well, the slope of this is 0, all right, but it's only 0 where the graph exists, and that is to the right of 0. So, interesting little constant function here. So, let's take a look then at number 52. 52 is a problem from the book that I'm gonna need another sheet of paper for that because I didn't want to retype up the whole problem 52 here. As you can see, we got a lot going on. So 52. I don't want to use the one that reveals the answer to you. That's like cheating. That'd be like you being the teacher. That would make life easy, wouldn't it? Okay, so 52. Kind of a cool problem. The spread of a rumor in a certain school is modeled by the equation. Man, rumors can spread fast in a school. Oh, I'm reading number 51. Oh, 51 would be a good one for you to try after this, though. Let's go to 52. The spread of flu in a certain school, that can spread fast too, probably not as fast as rumors. The school is modeled by the equation, so we got this equation. Let's interpret this, where P of T is the total number. Okay, so that's like our position function. That's not a rate at all. That's just a quantity. Is the total number of students infected T days after the flu first started to spread. So, A, estimate the initial number of students infected with this flu. Well, common sense would tell me the initial number infected, you know, I guess that's not necessarily true. The initial number at the school, but common sense would tell me this would be a pretty small number, perhaps even 1. But that would be at 0 days. So I can put 0 in here. So the exact number would, in theory, be 200 divided by 1 plus e to the 5 minus t. Now, one thing to keep in mind on this, flus don't spread at that rate. That is not a constant, this is not a constant function. What we would do is we would chart the number of students diagnosed with flu, and then we would try to fit a curve to it. And this curve fits close to, so we may get an answer that's not completely satisfying here. Estimate the initial, and of course it says estimate. So I'm just going to go 200 divided by, close my parentheses, 1 plus, I could even graph this, which wouldn't have been such a bad idea, second e to the 5 minus 0, our initial, or just 5. And we get 1.33. So our estimate would make sense to be, if this is number 52, our estimate would make sense if it was 1.33 to be 3. Now, or excuse me, to be 1. Silly. All right. So A, just fumbling for some paper here. So A is approximately 1 student. now. B, how fast is the flu spreading? Well, the flu is spreading. How fast? That would be our rate, and our rate is our derivative of this. So we want P prime of T. And that we could low-d high that. We could take the denominator and raise that to the negative first. I'm going to just low d high minus high d low. Now, low d high is 0. So I get minus high 200 d low. Derivative of low is e to the. Well, e to the's want to just be e to the. But we have to multiply by our baby function, which is 5 minus t. Derivative of 1 is 0, of course, plus derivative of. So this is times negative 1, all on 1 plus e to the 5 minus t squared. Low d high, 0, minus high d low over the square of the thing below, or we get 200 e to the 5 minus t on 1 plus e to the 5 minus t squared. That's our growth rate. Okay, so how fast is it spreading after 4 days? We just want P prime of 4. So bear with me here. Let's clear this guy out. Oops, clear this guy out. Second, quit. Clear. And I've got 200. Let's see. Alpha step one. I'm going to do this way. I've got 200 e to the, so second ln e to the 5 minus t. We're going to step out of that, but what do I want for t here? We're trying to find 4, so 5 minus 4, all on 1 plus second e to the 5 minus 4. I'm regretting something here. 5 minus 4, can I go back in here and second insert a parenthesis, and second insert a parenthesis, and now I need to raise that to the second down here. Does that look right? 200 e to the 5 minus 4. Okay, so we're trying to find the rate after 4 days, and we enter, and our rate, holy cow, the school is in an epidemic here. About 39.3 students per day. So B, 39.3 students per day. It says, when will the flu spread at its maximum rate? We want the maximum of this, the maximum from this derivative function. So I'm going to take that derivative function, and I'm going to go ahead and I'm going to go ahead and graph that thing and see what we get here. So we get y equals, again, I'm going to go alpha y equals, so I can enter it this way. Makes things a little bit easier on me. 200 second e to the, we've got 5 minus t, step out of there, step down here, and I've got parentheses, 1 plus second e to the 5 minus t, step out of that, close parentheses, raise to, a lot going on there, raise to the second. I don't know, I'm going to go window, I'm going to go 0. Makes sense to kind of start at 0, and let's let it run. This may be overkill. I'm going to let it run for a month and see if we get a max here. Anytime you're guessing a domain, probably a good idea to zoom fit. That's zoom 0. And we're thinking a little bit here. Hopefully we find a max on this. Ooh, we don't, oh man. Yep, we found, oh, of course we found a max right at the top, and we found it early. Hopefully that shows up. There it shows up right there. So I'm going to second calc max, second calc maximum. And this is our growth rate. I want left bound, enter, right bound. This isn't number of students. This is the derivative, or excuse me, this is the graph of our derivative. And I enter, and I get virtually 5 and 50. So what is that 5? That 5 is our number of days, and that 50 that we have is our students per day. So when will the rumor spread at its maximum rate? C, part 1 is max rate at t equals 5 days. And what is the maximum rate? Maximum rate is 50 students per day. So kind of a cool problem there. All right, so after 52, we are going to jump over to number 57. 57, the derivative of y equals 2 to the x is supposed to be 2 to the x. So let's check that out. Y equals 2 to the x. If this was e to the x, we would have y equals, it would just stay 2 to the x. And it wants to do that, but we have to compensate for not working in base e with an ln 2. So that is our derivative. The question is, does 2 to the x times ln 2 equal 2 to the x? Well, of course not, because ln 2 is a constant that's not equal to 1. Therefore, we are false. Okay, well, let's take a look here. 58. The derivative of e to the 2x is 2 ln 2 e to the 2. I don't know, let's find out. Let's go y equals e to the 2x. So our derivative of that, dy dx, or y prime, the derivative of e to the x wants to be e to the x. But now we have to take that times the derivative of the inside function, and I get times 2, or 2e to the 2x. So is that equal to 2 times ln e to the 2x? No, because e to the 2x is there, but 2 times ln 2 is not the same as 2. Okay, let's just continue here. If flu is spreading at this rate, which of the following is the initial number of persons infected? Is it pretty clear here that we're just going to put 0 in for t? I think that's pretty clear, and we're going to find an approximation here. Let's go. Which of the following is the domain of f prime x if f of x is this? If f of x is this, that graph increases forever but quits existing, only exists to the left of -3. So x is greater than or equal to -3. 61. Which of the following gives the derivative of this? Well, let's just find it. Let's go y equals the derivative. If this was ln, we'd want it to be 1 on 2x minus 3, but it's not ln, so we have to compensate with ln of our base 10, and we have to take the derivative of the baby times 2. So let's see. There it is. 2 on 2x minus 3 ln 10. And let's see, do I have space for 62 here? Which of the following gives the slope of the tangent line of the graph at x equals 2? Well, let's find it. Y prime equals, if this was e to the 1 minus x, it would want to be e to the 1 minus x. But it's not. It's 2 to the 1 minus x. We compensate with ln 2. And we take the inside derivative, -1. I'm going to put that in front. And now we want y prime when x is 2. When x is 2, I get -2 to the, when x is 2, negative first, ln 2, or I get the opposite of, this negative can go with the ln, I get the opposite of ln 2 all on 2. The opposite of ln 2 all on 2e. And there you have it. Hopefully that's helpful. That wraps up 4-4. Kind of a welcome relief with the exception of maybe a problem or two from 4-3. It's just we've got some new rules to learn. Okay, good luck to you. Stay tuned.